Welcome back to Beralia Grade 9 Mathematics class. We will now be starting with Chapter 2, which involves radicals and imaginary numbers. Lesson 2.1 will discuss some definitions, notations, and the laws of radicals. Okay, for Chapter 2, we have radicals and imaginary numbers. Lesson 2.1 will be roots of real numbers and the laws of radicals. We have several objectives for this. We want to define the nth root of a real number, and we will also be defining a complex number and defining a radical, then stating the laws of radicals. First, therefore, definition. The roots of real numbers are defined by the following statement. Nth root of x equals r if and only if r to the n equals x. Here, n is element natural number and n should be greater or equal to 2. Let's try to have the following notes. Number 1, if n is even, then we can only have x and r to be non-negative for us to have a real root. Non-negative here means it's either 0 or positive. That's for n even. If n is odd, then x and r can be any real number. This means that if n is odd here, x and r may be both positive or they may be both negative. It cannot be that if n is odd, this one is positive, this one is negative, or this one is negative, this one is positive. So that's the definition of the roots of a real number. Example, let's say if r squared equals 25, s cubed equals 8, and t to the 5th equals negative 32. Okay, what do we say here? That r, s, and t are roots. They are the real roots. That is, r is a square root of 25, s is a cube root of 8, and t is a fifth root of negative 32. Now, let's analyze what this is. Let's consider the nth root of x. Nth root of x is called our radical. This is the radical expression where n is called the index or order and x is called the radicand. This is called radical sign. Example, cube root of 120. For this radical expression, 3 is called index or order. 120 is called the radicand. And the whole thing here, cube root of 120 is called the radical expression. Let's note several things here. From this radical, nth root of x, number 1, if n is odd and x is any real number, then there is exactly one real nth root of x. Example, cube root of 125 is equal to 5. There's exactly one real cube root of 125. This is 5. if we have this cube root of negative 1, we have 25. This one is negative 5. Recall that cube root of 125 equals 5 means that 5 cube equals 125. And similarly, cube root of negative 125 equals negative 5 means negative 5 cube equals negative 125. We mentioned earlier that if this is an odd index, this number and this number should have the same sign. So positive, positive, negative, negative. What happens if n is even and x is positive? There are two real nth roots of x. One positive we call the principal nth root, written as nth root of x, and the other one negative, written as negative nth root of x. Example, square root of 25. Here 2 is even and this is positive. So we have the first root 5, that's the principal square root, and this will be the other negative root. Both of these are roots of 25 because 5 squared equals 25. Also, negative 5 squared equals 25. Let's have to be careful here. We cannot say that the square root of 25 is plus or minus 5. This is no. But if I ask you to tell me what are the square roots of 25, you will say 5 and negative 5. Okay? That's clear. What's the square root of 16? That is 4. Not plus or minus 4. But the square roots of 16 are 4 and negative 4. Suppose if n is even and x is negative, then there is no real nth root of x. We have a complex number. Our imaginary number I is defined as square root of negative 1 equals I. That is square root of negative 1 equals I, or I times I equals I squared equals negative 1. Example, square root of negative 25. The index is even and the radical is negative. Therefore, we do not have a real square root of negative 25. Instead, we have a complex root. We write this as 25 negative 1 equals 25 times I squared, and the square root here now is 5i. This is a complex number, imaginary number. This one means that 5i times 5i equals 5i squared, or this is 25 I squared. But since I squared is negative 1, we get 25 times negative 1, or that's negative 25. Here's a case where we have no real square root of this negative number. We will end this lesson by enumerating the laws of radicals and giving some example. If m and n are positive integers and x and y are positive whenever m or n is even, then we have the following. Number 1, nth root of x raised to the n is equal to x. Example, cube root of 5 cube is equal to 5. Next one, if we have here nth root of x times nth root of y, then this is equivalent to rewriting that as nth root of x times y. Example, we have cube root of x times cube root of 2z. We can rewrite this as one radical, and we have cube root of 2xz. Next one, we get nth root of x over y equals nth root of x over nth root of y. Example here, if we have here the fifth root of 2x over 3y, we can actually rewrite this as fifth root of 2x over the fifth root of 3y. The fourth law that we will consider is mth root of the nth root of x equals nth root of the nth root of x equals the product of m and then we have that radicand. Example, if we have 6th root of 25, we can rewrite this as either cube root of the square root of 25 or square root of the cube root of 25. We see here that the better form of this one should be this one here, because this inner radicand is a perfect square, and that's index 2. So if we simplify this, this is actually square root of 25 is 5, and then we still have that cube root there. However, here we cannot simplify this anymore because 25 is not a perfect cube. So the better form should be cube root of the square root instead of square root of the cube root. The last law that we will consider is when we have different indices. We are multiplying two radicals of different index. Let's assume that m and n are relatively prime, meaning they don't have any common element except 1. So we just have to get the LCM of these indices. So we have m times n, and then I will have this radicand here, mn divided by m. I will have an n here, correction factor, and mn divided by n. I will have an m here, and I will retain this radicand. So this actually means that the product of these two radicals with different index, we will have this common index and then have the correction factor. If we rewrite this in two radicals, radical form, this looks like mn x to the n, and this one cancels off and is actually the same here. Similarly, I can write this also as mn y to the m, and I will cancel m and we actually this. That's the reason why we have that correction factor there. Example, suppose I will have square root of 2 times cube root of 3. The index here is 2 and this one is 3. We cannot multiply 2 and 3 immediately, but instead we are going to have the LCD of 2 and 3, or LCM of 2 and 3 will be a 6, and I will write this radicand here, and then 6 divided by 2 will be 3, 6 divided by 3 will be 2. So this one will be our answer, or you can write it as 6 root of 2 cubed is 8 and 3 squared is 9, or this is 6 root of 72. Now we have some notes here relating our rational exponent before, let's say x to the 1 over n. This in radical form will now be nth root of x. Furthermore, if we have here x to the p over q, we can write this as x to the p raised to the 1 over q. And in radical form, this is the qth root of x to the p, which I can write as qth root of x to the p. Also, I can write this one here as x to the 1 over q raised to the p. So here, we have a qth root of x raised to the p. So we have a qth root of x raised to the p. These two are equivalent provided we have valid values for x. Here ends the laws of radicals, and the next lesson will allow us to simplify radicals. Thank you.